In the endless silent theatre of the cosmos, there are performers of every size. There are the brilliant, fleeting superstars, the blue giants that live fast and die young, in supernova explosions of unimaginable splendor. There are the steady, reliable mainstays, suns like our own, providing stable, life-giving light for billions of years. And then there are the quiet, unassuming stagehands of the galaxy. They are the red dwarfs, the most common type of star in the universe. For every sun-like star, there are at least 10 of these diminutive luminaries littering the Milky Way like faint, ruby-colored embers from a cosmic fire. For much of human history, they were entirely invisible to us, too dim to pierce the veil of our atmosphere and be seen by the naked eye. We imagined them as peaceful, ancient, and perhaps even gentle. Their lifespans are measured not in billions, but in trillions of years, far longer than the current age of the universe itself. They sip their hydrogen fuel with an almost supernatural patience, promising a stability that could in theory nurture life for eons. It was this very promise that drew our telescopes toward them in our accelerating search for another Earth, another cradle of biology. We believed the universe's most common homes might be its most welcoming. We were profoundly, terrifyingly mistaken. Because within these seemingly placid celestial bodies brews a temper of such ferocious and unpredictable violence that it redefines our understanding of what a star can do. Deep within the constellation Canis Venatici, the hunting dogs, lies a red dwarf star designated DG Canum Venaticorum. It is a faint speck just 36 light-years from Earth, a close neighbor in the grand scheme of the galactic neighborhood. Astronomers had turned the unblinking gaze of our finest observatories upon it, including the venerable Hubble Space Telescope, a sentinel in orbit for decades. They were not expecting a drama of cosmic proportions. They were conducting a survey, a patient cataloguing of stellar behavior, when they captured something that defied all previous models. The data streamed back to Earth, a torrent of numbers and light signatures painting a portrait of a cataclysmic, almost instantaneous event. The star erupted. This was not a gentle flicker or a modest solar flare. This was a tantrum of pure, unadulterated stellar rage. A colossal wave of superheated plasma, a coronal mass ejection, was unleashed from the star's turbulent surface. This titanic cloud of charged particles and twisted magnetic fields was expelled into space with a velocity that seemed impossible. It was clocked at an astonishing 2,400 kilometers per second. Let us pause to comprehend that figure. It is a velocity of more than 5 million miles per hour. A spaceship traveling at this speed could cross the distance between the Earth and the Moon in less than 2 minutes. It is a rate of travel so extreme, so mind-bendingly swift, that it challenges the very physics of how such blasts are supposed to accelerate. The energy released in this single fleeting moment was staggering thousands of times more powerful than the most extreme solar storm ever recorded from our own sun. And as scientists stared at the graphs, at the spectrographic analysis, a chilling realization began to dawn. Our galaxy's most common stars, the ones we thought were benign, are capable of a fury that could render any nearby world sterile. They are not gentle embers, they are cosmic powder kegs with an exceptionally short fuse. To truly understand the source of this terrifying power, we must journey into the heart of the star itself. Imagine our own sun, a familiar and life-sustaining sphere. Its interior is layered like an onion. At its core, a furnace of nuclear fusion generates energy. This energy travels outward through a dense, stable region called the radiative zone, a journey that can take a photon of light over 1,000,000 years to complete. Only in the outer third of the sun does the energy transport mechanism change. Here in the convective zone, hot plasma rises, cools, and sinks, much like water boiling in a pot. This churning motion is what drives our sun's magnetic field, and ultimately its solar flares and weather. A red dwarf, however, is a fundamentally different kind of beast. It possesses no such orderly layered structure. A red dwarf is fully convective. Think not of a pot of water boiling only at the surface, but a sphere where the boiling happens all the way down to the core. The entire star is a single, chaotic, tempestuous cauldron of roiling plasma. There is no stable radiative zone to calm the motions. From its deepest interior to its visible surface, the star is in a constant state of violent upheaval. This ceaseless globe-spanning churning has a profound effect on its magnetic field. It twists and stretches the magnetic field lines into incredibly complex and highly unstable configurations. To grasp the tension this creates, consider a simple analogy. Picture yourself holding a handful of rubber bands. These bands represent the star's magnetic field lines. Now begin to twist them. With each turn, you store more potential energy. The bands become taut, strained, and knotted together. This is what the red dwarf's relentless convection does to its magnetic field, twisting it for weeks, months, years, creating colossal ropes of magnetic tension. Eventually, the strain becomes too great. The tangled lines can no longer hold their form. They snap and reconnect in a simpler, lower energy state. The sudden release of all that stored potential energy is apocalyptic. The rubber bands breaking in your hand would produce a small sting, a faint sound. But when magnetic field lines spanning tens of thousands of kilometers snap, the energy release is equivalent to billions of hydrogen bombs detonating at once. This is the genesis of a superflare. This is magnetic reconnection on a star-slaying scale. The explosion of light and radiation is followed by the main event, the coronal mass ejection, the very plasma cannonball we observed. The star's own substance is hurled into space, a magnetized tsunami carrying with it the fury of a reconfiguring magnetic dynamo. The speed of 2,400 kilometers per second suggests a release of tension so profound, so immediate, that our current models struggle to contain it. It's as if the star didn't just snap a few rubber bands, but its entire magnetic architecture underwent a violent, instantaneous collapse and rebirth. This ferocious process is not an isolated incident. While our own sun produces a major flare perhaps once a decade, and a truly catastrophic one, once a century active red dwarfs can unleash these superflares on a weekly or even daily basis. They are perpetually angry, seething with a magnetic resentment born from their chaotic internal structures. And this brings us to the most unsettling part of this cosmic story, the implications for life. For decades, we have been captivated by the concept of the habitable zone. It is often called the Goldilocks Zone, a term that evokes a sense of comfort and providence. It represents the narrow orbital band around a star where the temperature is just right for liquid water to exist on a planet's surface. Not too hot that the oceans boil away, not too cold that they freeze solid. For a bright hot star like our Sun, this zone is located at a comfortable distance. Earth orbits at 150 million kilometers, far enough to be safe from the worst of the Sun's everyday outbursts. Our world is afforded a crucial buffer of space, but a red dwarf is small, cool, and exceedingly dim. To receive enough warmth to sustain liquid water, a planet must huddle incredibly close to its parent star. The habitable zone around a typical red dwarf is often 20 times closer than Earth's orbit is to the Sun. An Earth-like planet in such a system might have an orbital year that lasts only a few weeks or even a few days. It would be tidally locked with one side perpetually facing the star in endless day and the other trapped in an eternal frozen night. From the surface of this hypothetical world, its red sun would loom immense in the sky, a vast smouldering ruby dominating the heavens. It would be a world of permanent twilight and deep shadows. And it is here, in this intimate, close-in orbit, that the gentle promise of warmth becomes a deadly, inescapable trap. The Goldilocks Zone becomes the kill zone. A planet orbiting this closely is on the front lines, with no buffer, no distance to soften the blow of its star's rage. When the Red Dwarf unleashes a tantrum like the one we witnessed, that 2400 km/s blast of plasma is not a distant threat. It is an immediate world-ending catastrophe. The journey time for the plasma cloud to cross the tiny distance to the habitable planet would be measured not in days but in mere hours. Imagine standing on that alien world. The first sign of doom would be the flare itself. The giant red sun in the sky would suddenly brighten by a factor of 1,000, instantly bathing the dayside in a torrent of X-rays and ultraviolet radiation. This initial wave of hard radiation would be a sterilizing agent capable of scouring the surface of complex organic molecules. But that is only the prelude. Hours later, the main wall of plasma arrives. A planet's primary defense against such an onslaught is its magnetic field, its magnetosphere. This invisible shield, generated by a molten rotating core, deflects the stream of charged particles from a star, the stellar wind. Think of it as an umbrella in a rainstorm. Earth's magnetosphere is a sturdy, reliable umbrella, adept at shielding us from the sun's normal, gentle drizzle of particles. Even during a strong solar storm, our umbrella may flex and shudder. Auroras may light up the polar skies, but the shield largely holds. Now imagine that 2400 km/s plasma blast. This is not rain. It is not even a hurricane. It is a solid wall of water moving at supersonic speed. The umbrella of a magnetosphere, no matter how strong, would be instantaneously and violently compressed. The front of the shield would be pushed down to the planet's surface, and perhaps even below it. The entire defense system would collapse in an instant. With the shield gone, the full kinetic fury of the plasma cloud slams directly into the planet's upper atmosphere. The process that follows is known as atmospheric stripping. It is a relentless, brutal erosion of a world's air. The high-energy particles act like a sandblaster, colliding with atoms of nitrogen, oxygen, and water vapor, and imparting enough energy to kick them out of the planet's gravitational grasp forever. Molecule by molecule, the precious blanket of air is ripped away into the void. A single superflare might strip away only a small fraction. But these stars are not one-time offenders. They are chronic abusers. Week after week, month after month, the planet is battered by these tantrums. Each blast peels away another layer of its atmosphere, over geological timescales which are but a blink of an eye for a star that lives for trillions of years. The consequences are absolute. The atmosphere thins into a vacuum. With the air pressure gone, the oceans on the surface would violently boil away, the water vapor itself being stripped and lost to space. The world would be desiccated, its liquid lifeblood lost to the cosmos. What was once a temperate, water-rich world, a potential Eden, would be transformed into a barren, airless rock indistinguishable from our own moon or Mercury. Its surface, now unprotected, would be relentlessly sterilized by the star's constant flares and harsh radiation. The dream of a habitable world dies not with a whimper, but with a prolonged, agonizing scream. This terrifying scenario forces us to confront a profound and unsettling possibility. The Milky Way galaxy is home to perhaps 1 trillion stars. At least 75% of them, some 750 billion, are red dwarfs. This means that the vast majority of planets in our galaxy orbit these specific types of stars. The most common real estate in the cosmos is located in the most dangerous neighborhoods. Our search for extraterrestrial intelligence, our yearning to find that we are not alone, has naturally focused on these abundant systems. We have found promising candidates like Proxima Centauri b, the closest exoplanet to our own solar system orbiting a red dwarf. We have discovered entire systems of Earth-sized worlds, like the TRAPPIST-1 system, all huddled close to their small, cool parent star. We have dreamed of what life might be like on these worlds, but the evidence of these stellar tantrums paints a bleak picture. It suggests that these worlds might be cosmic mirages. They may tick all the boxes of the habitable zone on paper, possessing the right temperature for water, but in reality they may be trapped in a cycle of abuse so profound that the emergence of life, let alone its survival and evolution, is a near impossibility. This could be a partial answer to the great cosmic silence, the question posed by the physicist Enrico Fermi: where is everybody? Perhaps the universe is teeming with planets, but the vast majority of them are born into circumstances that are fundamentally hostile to life. Perhaps habitable worlds are not rare because the conditions for their formation are unique, but because the conditions for their long-term survival are. A planet doesn't just need the right ingredients for life. It needs a stable, peaceful parent star, a nurturing environment over billions of years. It needs cosmic luck. Is there then no hope for life around red dwarfs? The universe is rarely so simple, so black and white. Science thrives on nuance and on challenging its own conclusions. Perhaps some planets are more resilient than we imagine. A world with a significantly more massive iron core could, in theory, generate a magnetic field many times stronger than Earth's. This supermagnetosphere might be able to withstand the onslaught, acting as a more robust shield against the stellar fury. Or perhaps a planet could be born with an incredibly thick atmosphere, a vast reservoir of gas that could endure billions of years of stripping before it is finally depleted. Life might even find a way to exist underground or in the deep oceans, shielded from the radiation on the surface by kilometers of rock and water. But these are for now merely hopeful speculations, islands of possibility in a sea of troubling data. The 2400 km/s blast remains a stark warning. It is a demonstration of the raw, untamed power that governs these systems. It reminds us that the universe is not designed for our comfort or for life's convenience. The cosmos is a place of extremes of serene beauty and breathtaking violence, often existing side by side. The very same star that offers the warmth necessary for liquid water can also produce the fury that rips that water away. Our understanding of this phenomenon is still in its infancy. The discovery of this one monumental blast was a serendipitous event, a snapshot of a star caught in its most extreme moment. How common are such events? Do they happen on all red dwarfs or only the young and active ones? Do these stars eventually calm down as they age, offering a window of opportunity for life in their twilight years? These are the questions that drive us forward. They are the reason we build ever more powerful telescopes like the James Webb Space Telescope, now peering into the depths of space. This magnificent instrument has the power to analyze the light from distant stars as it passes through the atmospheres of their orbiting planets. It can search for the chemical fingerprints of oxygen, methane, and water vapor. It can, for the first time in human history, tell us if these worlds huddled close to their red dwarf suns even have atmospheres left to study. The coming years will be a period of revelation. We will either find barren, airless rocks confirming our worst fears, or we will find worlds that have somehow defied the odds, worlds that have clung to their atmospheres against all expectations. Either discovery will be a profound chapter in the human story. If they are barren, it will underscore the preciousness and perhaps the rarity of our own world. It will reinforce the notion that our calm, stable sun is a gift of immense cosmic fortune. It will tell us that Earth is not just a home, but a sanctuary, a tranquil harbor in a galaxy filled with stellar storms. But if we find a world that has survived a world with air and water orbiting one of these tempestuous red dwarfs, then that will tell us something even more profound. It will tell us that life may be more tenacious and planets more resilient than we ever dreamed. It will suggest that nature has found ways to overcome even this level of celestial violence. Until then, we are left to gaze up at the night sky, at the countless faint points of light that represent these red dwarf stars. We no longer see them as merely placid, gentle embers. We see them for what they are: complex, dynamic, and capable of a terrifying majesty. They are the silent majority of the cosmos, a family of stars whose true nature we are only just beginning to comprehend. And within their fiery hearts and furious tantrums lies a crucial clue not just to the nature of stars, but to the ultimate question of whether we are in this vast and violent universe truly alone. The tantrum of a single distant star has sent a shockwave through our assumptions, forcing us to look at the universe with a new sense of humility and a deeper sense of awe. The quietest corners of the cosmos may in fact be the most tumultuous, and the search for life has become a search not just for warmth, but for shelter from the storm.